All right. So we're going to jump into something that you probably already pretty deep into yourself, linear transformers.
hmm
And specifically, there's been a lot of buzz around, how do we make these things really efficient for long sequences,
Right.
especially for tasks like in-context retrieval?
Yeah, absolutely.
So, this is where these models like Mamba2 and DeltaNet are really trying to, kind of push the boundaries.
Yeah, it's definitely a challenge that's sort of at the forefront right now.
Yeah.
How do we get the power of transformers without, them kind of choking on long sequences?
Exactly. So you shared this paper with me, Gated Delta Networks, Improving Mamba 2 with Delta Rule,
Mm.
plus, a couple of articles about it. And, what I was really curious about was, how do these new models...
Oh, hey there, what's up?
Before jumping, can we discuss the difference between delta rule and backpropagation?
Oh, that's a great question. Okay, let's unpack this.
Yeah, it's actually a really important distinction to make.
So the Delta Rule is a way to update a model's memory.
Whereas backpropagation is how a model learns in general.
Right, backpropagation is this broader process where we compute the gradient of the loss.
And use that to update the model's weights.
It's about how a model adjusts all of its parameters.
The delta rule is more specific. It's a way of updating the model's state based on the new information that comes in.
Yeah, the Delta Rule is like, how do I update my memory right now?
While backpropagation is like, how do I learn and improve overall?
So the Delta Rule is actually part of the forward pass, during processing.
Exactly. It's a local update rule that happens on each time step.
And backpropagation is, over the whole training set globally.
Right. There are different levels of how the model updates its parameters.
So like we've been saying, the gated delta rule is a new twist on that memory update.
And later we'll discuss how this is like a type of online learning.
Which is a way of learning on the fly as the data comes in.
We'll see how that perspective relates to backpropagation as well.
Does that make sense for you?
I hope that helps clarify the difference.
All right, so where were we before that great question?
Let's get back to our comparison of transformers.
Yeah, but let's start with the basics.
Traditional transformers, they're very powerful, but they can be really computationally expensive. And that's because of how self-attention scales with the sequence length.
Right, that quadratic scaling could be a real problem.
Exactly. So linear transformers try to get around that.
Okay.
By using some clever tricks to achieve linear complexity.
So the cost doesn't explode as the sequence gets longer?
Exactly. Now, early on, linear transformers, they kind of struggled to match the performance of traditional transformers. But models like Mamba2 and DeltaNet have started to change that.
Okay, so let's talk about those.
Sure.
So Mamba2, first, it's all about this gating, right?
Yeah, that's a good way to put it.
Yeah.
So Mamba2, it uses a gated update rule to manage its memory, sort of like how LSTMs work.
Okay.
And this allows it to gradually forget information, which is really important for long sequences.
So it's not just holding on to everything it sees.
Right. It's kind of like slowly dimming the lights on past memories so it can focus on what's happening right now.
That makes sense.
Yeah.
But the paper mentions a drawback with Mamba2. And that is that it forgets everything equally. It's not very precise.
Right.
It's like turning off all the lights in the room when you only need one of them off.
It's a great analogy.
Yeah.
And that's where DeltaNet comes in.
Okay.
It takes a more surgical approach, you could say. Instead of dimming the lights, it's more like replacing a specific bulb.
So it's using the delta rule to selectively update its memory.
Exactly.
Replacing outdated information with the new stuff.
Precisely, DeltaNet's strength is its precision, but it does come at a cost.
What's that?
It's not as good at quickly forgetting irrelevant information when the context changes really abruptly.
Okay, so Mamba2 is good at the gradual forgetting, but not precise. DeltaNet is precise, but not great at rapid forgetting.
Right.
So gated delta networks, or as the paper calls it, gated DeltaNet, is trying to combine the best of both worlds.
Exactly. It's like having both a dimmer switch and a precision editor for its memory.
I like that. So how does it actually do that?
Well, the key is the gated delta rule,
Okay.
which adds a layer of control on top of the traditional delta rule.
Okay.
And this lets gated DeltaNet rapidly forget irrelevant information and selectively update specific content.
Okay, but this all sounds pretty computationally intense.
Yeah.
How do they make it efficient?
Well, they cleverly use techniques like chunkwise parallelism and the WY representation.
Okay.
But to really understand why this gated delta rule works so well, we need to delve a little deeper
Okay.
into how it actually addresses the core challenges of memory management in these linear transformers.
That's what I was hoping we'd get into.
Yeah.
I think as LLM experts, sometimes we take for granted how these models learn and update their internal representations.
It's easy to get caught up in the latest architectures and forget the fundamental principles.
Right.
But those principles are what make these innovations like Gated DeltaNet so exciting.
Yeah, so let's unpack those principles.
Okay.
So linear transformers, they process information sequentially, right? Kind of like reading a book word by word.
Exactly. And as they're processing that information,
Yeah.
they need to store and update a representation of what they've seen so
Yeah.
far.
Mhm.
And that's where the state of the network comes in.
And that state is constantly being updated based on the new information coming in.
That's right. And the way that state is updated is determined by what we call the update rule.
Okay.
Now, traditional linear transformers, they use a simple additive rule, which can be problematic.
Problematic hat.
Well, it can lead to something called catastrophic forgetting.
Okay.
Imagine you're trying to add new information to a whiteboard that's already full. You have to erase something to make space.
So you risk forgetting important old information when you encounter new information.
Exactly. And that's where the delta rule comes in.
Okay.
Instead of just adding information on top of what's already there, it selectively updates specific parts of the state based on the input.
Okay.
It's more like editing a document than just writing on a whiteboard.
So you can change specific parts without erasing everything else.
Precisely. And the gated delta rule takes us a step further
Okay.
by adding what's called a gating mechanism. It's like having a dimmer switch that controls how much the state is updated.
So it could be really subtle or really dramatic with its updates?
You got it.
Okay.
This gives the model much finer control over how it manages its memory, allowing it to retain important information for longer
Okay.
and avoid those catastrophic forgetting scenarios.
So the gated delta rule isn't just about adding information. It's about strategically updating and managing the model's memory.
You got it. It's a more nuanced and sophisticated way of handling the flow of information within the model.
Now, I know we have some real LLM experts listening, and they're probably itching to see the actual equation behind this gated delta rule.
All right, let's take a look.
Okay.
So the equation for the gated delta rule is
Okay.
Saint equals ST1 times TAC T chi T plus AST T chi TT.
All right.
Don't let all the symbols scare you. It's actually pretty intuitive.
Okay, I'm going to break it down for us. What's going on in this equation?
Okay, so first we have Saint, which represents the state of the network at the current time step. Thinking this as the model's current understanding of everything it has processed so far.
So like a snapshot of the model's memory at that particular moment.
Exactly. And on the right side of the equation, we have the update rule itself, which tells us how to calculate this current state based on the previous state and the new information coming in.
Okay, so let's start unpacking that right side.
All right.
So we have ST1, which I'm assuming is the state from the previous time step.
You got it. So we're taking the model's previous understanding and updating it.
Okay, and then things get a little interesting inside the parentheses. So we've got at, which you mentioned earlier, is kind of like a dimmer switch.
Right. At is a value between 0 and 1 that controls the overall strength of the update.
Okay.
A higher at means a stronger update, while a lower at means a weaker update.
So the model can fine-tune how much it lets the new information influence its existing memory.
Exactly. And then we have also a value between 0 and 1.
Okay.
And this one controls how much of the old information associated with a particular key is replaced by new information.
And I'm guessing newtist is that key we've been talking about? The way the model organizes its memories.
Precisely think of kati as a label for a specific piece of information. It's like the index card you'd use to find a specific book in a library.
Okay, so the model uses these keys to retrieve specific memories.
Yeah, now the term, I can answer T.
Okay.
That's what does the actual updating. It modifies the part of the state that's associated with the key IT.
And the strength of that modification is determined by F.
Exactly. Finally, we add VTT, which represents the new information associated with the key IT.
Okay.
So the model is selectively updating its memory based on the new information and the keys it's using to organize that information.
Okay. I think I'm starting to see how all these pieces fit together here.
Yeah,
But, before we move on, I want to connect this back to our listeners.
sure.
Why should someone working with LLMs care about all this technical details?
Yeah.
What's the big picture significance of this gated delta rule?
That's a great question. I think understanding how this rule works gives you a much deeper appreciation for why these new linear transformers are so powerful and efficient, especially if you're working on tasks that require processing very long sequences or tasks where in-context retrieval is really critical.
So it's not just about using the models, it's about understanding them deeply enough to push the boundaries.
Exactly. It's about becoming a more effective LLM practitioner, whether you're building new models, optimizing existing ones, or just using them to solve real-world problems.
I love that.
Yeah.
Okay, so we've covered a lot of ground. We've talked about the limitations of traditional transformers, the rise of linear transformers, and this exciting new gated delta rule that powers gated DeltaNet.
Yeah, it's been a great discussion so far.
But the paper doesn't stop there. It also delves into some really fascinating hybrid architectures
Oh, yeah. That's where things get even more interesting.
that combine gated DeltaNet with other approaches. And we'll dive into those exciting developments in the next part of our deep dive.
So these hybrid architectures, they really showcase the potential of combining different approaches to memory management.
Okay, so you're saying it's not just about, finding one perfect update rule to rule them all.
Right. It's more about understanding the strengths and weaknesses of different approaches
Okay.
and then strategically combining them.
So what kind of hybrid architectures are we talking about here?
Well, the paper explores two main types.
Okay.
The first combines gated DeltaNet layers with something called sliding window attention layers.
Now, sliding window attention, just to remind our listeners, is a technique that helps the model focus on the words that are closest to the word it's currently processing.
Right.
Kind of like narrowing its field of vision to the most relevant context.
Exactly. And it's really good at capturing those local dependencies within a sequence, something that linear transformers sometimes struggle with.
So you're essentially combining gated DeltaNet's, long-range memory with the local context awareness of sliding window attention.
Right.
It's like having a wide-angle lens and a zoom lens all in one.
That's a great way to put it. And the results show that this type of hybrid model is really effective for tasks that need both a global and a local understanding of the input sequence.
Interesting. What about the second type of hybrid architecture?
The second type combines gated DeltaNet with, you guessed it,
Okay.
Mamba2 layers.
Bringing back the gating guru.
That's right.
I'm curious, what's the thinking behind that combination?
Well, Mamba2's gradual forgetting mechanism can actually help smooth out the updates made by the gated delta rule.
Okay.
It's kind of like adding a shock absorber to the system.
So it makes the learning process more stable and robust.
Exactly. And what's really impressive is that these hybrid models, they often outperform even the standalone gated DeltaNet model.
So better performance and I'm guessing more efficient training as well.
You got it. The hybrid models tend to converge faster, meaning they need less data and computation to achieve high performance.
Now that's what I call the win-win. Less compute and better results.
It really highlights the power of carefully considering the interplay between different components in these models.
Stepping back for a moment, what strikes me is that this whole line of research really challenges our traditional assumptions about how memory works in LLMs. We're moving away from this idea of, simply cramming in as much information as possible.
Right.
And towards a more nuanced and strategic approach to memory management.
That's a great observation. It's not just about memorizing everything. It's about remembering the right things,
Right.
knowing how to access that information effectively.
And that's where these new update rules, like the gated delta rule, really shine. They give us the tools to be much more selective and deliberate about how we manage the information flow within these models.
It's a real paradigm shift in how we think about memory and learning in LLMs.
Yeah.
And I think it's going to unlock a whole new wave of innovation in the field.
I completely agree now for our LAM expert listeners out there.
Yeah.
I'm curious to get your take on what this means for the future of update rules. We've seen how well combining existing rules can work,
Right.
but what about designing entirely new rules from scratch?
That's a fascinating question.
Yeah.
We're already seeing some exciting work in that area.
Okay.
For example, researchers are exploring update rules that dynamically adapt based on the task or the type of information being processed.
So instead of having one fixed update rule for every situation, the model could learn to adjust its memory management strategy on the fly.
Exactly. It's like having a toolbox full of different memory tools.
Yeah.
And the model can choose the right tool for the job.
That's incredible. I'm imagining a future where we have these libraries of specialized update rules.
Yeah.
Each optimized for specific tasks or types of data.
And we could even imagine models that learn to combine these rules in creative ways, discovering entirely new and more efficient ways to manage information.
It's like giving LLMs the ability to not only learn from data, but also to learn how to learn more effectively.
Yeah.
That's a powerful idea.
It is. It's a bit mind-bending when you think about it, but it's a testament to the incredible ingenuity of the researchers working in this field.
Yeah, they're constantly pushing the boundaries of what we thought was possible. Okay, so we've talked about gated delta networks, this exciting new gated delta rule, and the potential of hybrid architectures. We've also touched on the broader implications for the future of update rules and the evolution of LLM memory management.
It's been a fascinating discussion so far.
But before we get too carried away with the future, I want to make sure we circle back to the present.
Okay.
And talk about what this all means for someone working with LLMs today.
Yeah.
What are the key takeaways that they can apply in their own work?
That's a great point. I think one of the most important takeaways is that understanding how these update rules work can give you a real competitive edge.
In what way?
Well, it can help you make more informed decisions about which models and architectures to use for different tasks.
So for example, if I'm working on a task that involves a lot of in-context retrieval, knowing about gated DeltaNet's ability to avoid memory collisions might influence my choice of model.
Exactly. And even if you're not building models from scratch, understanding these principles can help you fine-tune existing models more effectively, or even troubleshoot issues that might arise from memory limitations.
It's like having a deeper understanding of how the engine works, even if you're not the one building the car. It makes you a better driver.
That's a great analogy. It's about empowering yourself to become a more knowledgeable and skillful LLM practitioner.
I love that. Okay, so we've covered a lot of ground today. We've talked about the challenges of memory management in LLMs, explored these innovative new update rules, and delved into the world of hybrid architectures.
And we've connected it all back to why it matters for anyone working with LLMs, whether you're a seasoned researcher or just starting out.
But our deep dive isn't over yet. We've still got one more fascinating aspect to explore the results.
Oh, yeah.
How does gated DeltaNet actually perform in practice, and does it live up to the hype we'll find out in the final part of our deep dive?
All right, so it's time to put gated DeltaNet to the test.
Right, let's see if it can walk the walk after all that talk. I know our LLM expert listeners are eager to see how this all translates into real-world performance.
Well, the paper presents some pretty compelling results.
Okay.
They tested gated DeltaNet on a whole range of tasks, including language modeling, common sense reasoning, and of course, in-context retrieval.
How did it do?
Across the board, gated DeltaNet consistently outperforms both Mamba2 and DeltaNet.
Okay.
And we're not just talking about, marginal improvements here.
Right.
In many cases, it's a significant leap forward in performance.
So it's not just a theoretical improvement, it actually delivers in practice.
Exactly. And it gets even more interesting when you look at the results for in-context retrieval.
Okay.
This is where gated DeltaNet really shines.
Now, we talked earlier about how gated DeltaNet is designed to avoid those memory collisions that can happen when linear transformers try to store too much information.
Right.
Did that actually play out in the results?
Absolutely. The paper shows that gated DeltaNet's flexible memory management gives it a real edge in those in-context retrieval tasks. It's able to hold onto a lot of context and then quickly access the right information at the right time.
I'm looking at the results here for the SNIH benchmark. That's a pretty tough test for in-context retrieval, right?
It is. It's designed to mimic the challenges of real-world data where the context can be very noisy and unpredictable.
And it looks like DeltaNet struggles a bit with this benchmark.
Yeah.
But gated DeltaNet handles it much more effectively.
Exactly. That's because DeltaNet, with its focus on precise updates, can sometimes get bogged down when the context is constantly changing. Gated DeltaNet, in the other hand, can quickly adapt and forget irrelevant information, making it much more robust.
So it's a real testament to the power of having both that precision editing capability and that ability to just quickly clear out the clutter.
I agree. It's the best of both worlds.
Okay, so the results are impressive. Gated DeltaNet outperforms existing models, particularly in these challenging in-context retrieval tasks. But what does this all mean for someone working with LLMs today?
Well, I think the most important takeaway is that gated DeltaNet works represent a major step forward in making linear transformers even more powerful and versatile.
Okay.
And this is really just the beginning.
What do you mean?
This research opens up a whole new way of thinking about how we design and manage memory in these models. It's not just about gated DeltaNet itself. It's about the broader implications for the future of LLM development.
So you're saying this could spark a whole wave of innovation in memory management techniques?
Absolutely. We're already seeing researchers exploring new update rules inspired by this work.
Okay.
Rules that are even more adaptable, efficient, and tailored to specific tasks.
So this is more than just a cool new model. It's a potential catalyst for a whole new generation of LLMs.
Exactly. And I think that's what makes this research so exciting. It's not just about, incremental improvement.
Right.
It's about fundamentally changing how we approach a core challenge in the field.
That's a great point. This has been a fantastic deep dive.
Yeah, it's been fun.
We've covered a lot of ground, from the basics of linear transformers to the intricacies of the gated delta rule, to the exciting potential of hybrid architectures.
Yeah,
And we've connected it all back to why it matters for anyone working with LLMs.
that's right.
Before we wrap up, I want to leave our listeners with a final thought to ponder.
Okay.
If combining different update rules like this can lead to such impressive results, what other combinations might we explore? Could we design update rules that adapt dynamically based on the task at hand?
Yeah.
Or the type of information being processed?
That's a great question to leave our listeners with. The possibilities are truly endless.
Yeah.
I think we're just scratching the surface of what's possible with memory management in LLMs. And I, for one, can't wait to see what the future holds.
Well said. Thanks for joining us on this deep dive. Until next time, keep exploring and keep pushing the boundaries of what's possible with LLMs.